to find the same thing. Am I right? Yeah, but what if, remember what I taught last week, right? What if it's not the bigger circle? What if in a situation that what you're calculating is the smaller circle? If you don't use 3D mode circle, you're done, right? All of a sudden, your structure will fail in what? Will fail in what? Tresca's criteria, in shear. Okay, that's why you have to check. Okay, so I think what we are doing down here, once we finish this course, okay, this final week of lecture, whenever you design any structure, okay, that you're that they're involved in terms of sizing, in terms of failure, follow this procedure. You won't go wrong. Okay, you won't go wrong. All right, right. So now we know. So now we have identified the maximum shearing stress. Okay, let me. Now we have found that tau max is equal to tau max xz, which is equal to tau max zx, and is the in plane. Is the in plane shearing stress. Okay, is the in plane, right? Not the, so now we know what to calculate, right? Okay, so from here, what we need to determine, there are two things that we determine. So in the analysis, so from here, where do we go? So you say, Eugene, we have been here for almost 1 hour, 20 minutes. What did we conclude? Okay, so what we conclude is this. Okay, what we conclude is this. Okay, we have to find, so we know the in plane, so we also have to find, okay, so we have to, so okay, so we have to find what is our stress A and stress B value. Why? Because then we can equate to stress U is equal to stress A minus stress B. So that's the first thing we have to do. Okay. We can also materials property. Okay. Now I'm going to show you material property data from material properties handbook. What do you see? Okay. So again, this is on I posted this. I'll show you. So this I got from the textbook. Okay. So typical properties that you will get. Okay, typical properties you will get. So what we will see over here. Okay. So what we are designing is for ductile material. So ductile material, we don't look at ultimate strength. Okay. We look at EU for ductile material. So what you observe is for tension, there are a lot of values. Right? You can see all this wow tension there. In compression, you only have what? You only have two values. Yes or no? You have no. So don't be like me when I was young. I need the structures under shear. I deliberately only choose this one. Okay, I only choose this one. For example, why I choose this one? I told the principal engineer I have the shear stress. Okay, and I make a fool of myself. I was in the UK then. Okay, I make a fool of myself. You. Okay, she said no. You have to find the shear stress. Okay, so back in Canada while teaching this course, okay, this is like more than 10 years ago now, I realized that you can use this also, but you have to declare. Okay, so if you're going to use the quench and tempered AI ASTM A709, you just have to mention this. So based on tau Tresca, okay, Tresca, I don't know how to spell Tresca now. Okay, so based on Tresca, right, the shear max is equal to 690 divided by what? 2. Okay. So you have to declare. It's okay to use any values that you don't have the shearing stress, but you have to know what criteria you're bringing in. I'm going to use Tresca, 690 divided by 2. You're good to go. Are we clear? Okay, don't use like, okay, so I think only this material is only good for us. Okay, so I only can use this because I have to share. Not necessarily true. Okay, state your assumptions. Okay, so if you are not sure, maybe you can put a safety factor of 1.3. Okay, we're not, it's safe enough. Structures, optimum structures that you know the stress state, okay, you can use a safety factor of 1.3. If you're unsure of the analysis, you don't know the stress state, you use a safety factor of 10. Right? You are not sure. Okay, so but don't use a, civil engineers can use a safety factor of 10. Mechanical engineers, we can't because we do things that it moves. Okay, so imagine you 10 times over design. On civil engineering aspect, yeah, the bridge is over designed is good, it won't collapse. Yeah, but material is getting more expensive. Okay. Right. So now we know our analysis now. Okay. So now we know where to head. We have to find stress A, stress B value, and we have to determine our tau max, which is also equal to the what? Radius of the biggest or larger circle. Okay. Okay. So just to quickly recap what we have been doing. Okay. So we were solving a shaft problem. Okay. Very simple loading, axial load, torque, and bending moment. We have to understand, so we have to integrate what we've learned before. We have to know the normal stresses, okay, how it distribute, the shearing stress due to shear force, how it distribute, and the torque. Then after that, we have to do failure analysis, which element will fail, right? And then we see whether it's positive or negative shear. But hold on, it's a good part. Wait, then we construct 3D mold circle, then we determine the maximum whether are we dealing with in plane or out plane. Now, this is where I forget to highlight is my bad. Okay, worship the maker. I don't know what it means over there. Now, what if you got the shearing stress wrong? Wrong direction. I repeat, wrong direction. Okay, so if you got the shearing stress in the wrong direction, it will not affect the diameter of the circle. So what do I mean? Okay, so let's say now, over here, you did not know, okay? So you pick this is your XW, means wrong, okay? XW. And down here is your ZW. ZW means wrong, okay? When you draw the line, right, it will still generate the biggest diameter. So what I'm trying to say is for homogeneous, for isotropic materials, okay, isotropic means same stress or same strength in all condition. Okay, so I write down here same strength in all direction. Right. It is okay or it is valid to assume wrong shear stress direction in torsion only. If you have shear force, it's very dangerous. Okay, I don't have time to show you why. Okay, but you can't do it when there's a shear force. Okay, it's very risky. Okay, right? So for isotropic, it's okay. Now for anisotropic, okay, anisotropic material. So anisotropic is carbon fiber reinforced, okay, plastic, okay, which I do quite a bit of research on it. It is what? Invalid to get the wrong shear stress orientation. Okay. So for homogeneous, it's okay, but for an isotropic, you can't do that. Okay, just to highlight. Okay. Now this is the first time you've seen this. Okay. Yeah, I don't have time to explain this, but do not do this if, let's say, you have reinforced concrete with steel. You can't do this. Okay. You have to know the actual direction, or not, your reinforced steel will be in the wrong direction. Okay, in the wrong direction. Okay. Right. So from here, all we need to put in now are numbers. You guys are, yeah, right, Eugene, numbers. Okay, so all you have to do now is just put in numbers, okay, and solve it. Okay, and we have to solve this using Excel. Okay, we have to solve this using Excel. So do y'all need a break now? Y'all want a break now or want a break at 10:45? Anyone? You need a break now? Or 10:45 is okay? Anyone?
Can we just finish this example first?
It will take about an hour. Okay, go for your break now. Come back at 10:45. Okay, come back at 10:45. Okay, I'll stop recording now.